I'll show you a segment of Dr. David Deutsch, pictured here, in interview with Kurt Jabungo, where David addresses criticisms to his popularized many worlds interpretation. David Deutsch is a British physicist, philosopher, and computer scientist. He's considered the father of quantum computing. He was born in Haifa, Israel, and later moved to the UK. He's considered a key advocate of many worlds interpretation because it addresses quantum paradoxes without the need for wave function collapse. This is considered a continuation of the previous video. Our maestro, Donald Trump, prepares us for a future of quantum computing.
Instead of, like in Everett's way of doing it, you had one world and then three worlds, let's say, or one world and a million worlds. Whereas what really happens is that there isn't really one world. Even when you have a single pure state of a system,
yes,
it's still the state of its being at a particular of a particle being at a particular place also includes within that unity there is a diversity that the more the particle is in one place, the more its momentum is different. So there is no such thing as there being one world at the beginning. There's always a continuum of universes or worlds, but they're only worth calling universes when they subsequently evolve independently of each other. And typically that happens when there's been a measurement process. So before there's a measurement, when there's just a particle, a wave packet sitting there, yes, there's lots of momenta, there's lots of positions all happening at once. Nothing is ever sharp, but you can't say that there are different momenta in different universes because all those universes are interacting with each other. So you should only call something a universe when it is causally autonomous. In other words, it's behaving exactly as it would if the others were not there. And that's what happens after a measure. So it's been a bit long-winded, but the answer is that the rejoining of universes is what happens in an interference experiment. And during the interference experiment, you can't speak of universes because the different branches are affecting each other. The interference is precisely the fact that that the different paths of a single photon around an interferometer, they're not behaving as if the other were not there. So when they come together, they do something completely different if the other one is there from what they would do if the other one weren't there. That's the whole interference phenomenon. So the picture you can have in mind is that there's a continuum in some kind of entity that's a bit like space-time, but in Hilbert space or something.
Sure.
In the multiverse, which we don't know how to classify mathematically yet, but. And then that continuum just differentiates itself into two. And as it's differentiating, there is no moment of split. What happens is that branch A is affecting branch B less and less. And when they have separated enough, like when you've made the measurement and you've copied it.
Delving into a transcript of the video, Susskind's objections. Objection 1. Branches can recombine, interference, and rejoining universes. In quantum theory, branches aren't always completely separate. They can recombine or interfere with each other, like the double-slit interference pattern. This challenges the many worlds interpretation idea of distinct, non-interacting worlds that split off permanently. If branches can merge back, how does many worlds interpretation make sense? It seems to undermine the notion of truly separate universes. Speaker agrees this is a valid point, but explains it has been addressed by viewing branches as emerging properties rather than fundamental ones in a theory. This refinement came in the 1980s, with the speaker mentioning their own early flawed attempts in the late 1970s, early 80s, crediting philosophers for clarifying it. Everett's original view treated measurements as creating discrete branches, but this isn't an oversimplification. In reality, quantum states are always a continuum, a superposition of possibilities. There is no such thing as a single, sharp world at the start. Unity and diversity coexist in a wave function. You can only call something a universe or branch when it evolves independently of others. It's causally autonomous. This happens after a measurement when interactions between possibilities become negligible, down to 10 to the 100th levels of influence. Before that, everything is intertwined in the multiverse. Recombination happens in interference. Rejoining isn't a problem. It's exactly what occurs in interference experiments. During interference, you can't talk about separate universes because the paths affect each other. Branches rejoin when possibilities interact strongly again. There is no discrete moment of splitting. Instead, the multiverse, a continuum of Hilbert space, gradually differentiates with branches affecting each less over time. Think of the multiverse as a fluid entity, like a continuum in the space-time, but in quantum terms. It doesn't snap into separate worlds. It differentiates gradually. Interference is when branches aren't yet autonomous. They behave differently because the others are present. In short, this resolves the objection by making branches dynamic and emergent, not rigid. The speaker ties this back to Everett, but notes that Everett focused on measurement endpoints, not the in-between dynamics when branches form. Objection 2. Probabilities and unequal irrational splits, the Born rule. Many worlds interpretation struggles with probabilities from the Born rule, which says that the probability of an outcome is the square of its wave function amplitude. If a measurement has an equal odds, 50-50, you can imagine a universe splitting into two equal branches. But what about the unequal odds of 1/3 and 2/3? Does the universe split into three branches with two identical ones for the 2/3 side? What about the irrational probabilities, a rational number 2 divided by 2, which can't be neatly divided into integer worlds? This seems messy and undefined. The transcript doesn't dive deeply into this one, but implicitly ties it into the first objection via emergent continuum view of branches. Speaker notes this has answers going back to Everett and refinements in the 1980s. Here the breakdown based on transcripts logic and standard many worlds interpretation defenses. No need for integer splits. The splitting into equal worlds is a misconception from popularized many worlds interpretation descriptions. Branches aren't discrete, countable things, like one world becoming three. Instead, the multiverse is a continuum, and probabilities emerge from the density or measure of branches in that continuum. Similar to how a wave function amplitude dictates likelihood, the branches only count as separate when they're autonomous post-measurement. The Born rule arises naturally from how superpositions decoherence due to interactions with the environment, creating effectively independent branches with weights matching observed probabilities. Overall, these resolutions make many worlds interpretation more elegant. The multiverse is fundamental, and worlds are just useful approximations for autonomous regions. The speaker emphasizes that in non-measurement cases, can't even talk about separate worlds because everything interacts. Why do skeptics like Susskind say these haven't been answered? The speaker speculates it could be that Susskind is talking to rudimentary many world interpretation advocates, not asking the right people, not listening, engaging deeply. Quantum foundations aren't mainstream in fundamental physics. Many experts focus on practical applications like Susskind's string theory work and may not follow philosophical refinements closely. The 1980s work on decoherence and emergence came partly from philosophers and theorists outside the core physics community, so it might not penetrate all circles. There could be a type of interpretational bias. Skeptics often stick to critiques of Everett's 1957 version without updating for later developments. Susskind has publicly critiqued many worlds interpretation elsewhere, emphasizing issues like or infinities, addressing the communication gaps. Sometimes debates can feel like they're talking past each other, not uncommon in these spheres.
You've been chosen.